start this lecture 3. So today we're continuing the introduction to thermodynamics. Well, I guess you could call it introduction to advanced thermodynamics. Fundamental relation and equations of state continued. It's mainly from Callen chapter 3. There's a little bit from maths book that I like, Advanced Calculus, by Professor Widder from Harvard University about 30 years ago or something. This book, by the way, is another one of those Dover publications I told you about. Dover, that the publishing house trawls through a century worth of books that have gone out of print and whose copyright is expired, and they purchase the copyright and they republish the books very cheaply. And this is a very good one, I think, for advanced calculus. So it's a step above the vector calculus that you learned last year in MP2. And I really like the way that it's written. It's a proper maths book. It's not too heavy on the analysis. Okay, it's nicely written and it's easy to read and very clear. Okay, so we're doing 5 main points, maybe just 4. In lecture 2, in the last lecture, we saw that the equations of state are the first derivatives of the fundamental relation, and that's a kind of a top-down approach. We also saw 2 ways in which the fundamental relation can be reconstructed from 2 or 3 equations of state, which is a kind of a bottom-up approach. Right? So if you have this picture clear in your mind, then you have a roadmap for the calculation that you're doing. You know, for example, that if you're working with equations of state, you're going kind of bottom up to get an overarching fundamental relation. So you know the purpose or the direction of your calculation. But the question is, something that we didn't actually answer is, why is this possible and what is the significance of that? Now, this is going to be a mathematical answer, not the physical answer. So we're going to ask about like a mathematical question here, and just some relevant mathematical theorems from this book here. Now, the second thing that we'll do is, well, if you look at these theorems, then the mathematics suggests how, given one equation of state, you can find another one. Okay. So if you've only got one equation of state, how can you actually use the knowledge of the mathematics to derive a second one? Okay. And we'll actually work through an example, do by example, and it's the van der Waals equation of state. How many of you have heard of the van der Waals equation of state? Can you put your hand up? Van der Waals? It's not van der Waals equation of state. Yeah, Shinji, I know you've heard it. Stick your hand up. Thank you. Good. So we'll have a look at that. And the van der Waals equation of state relates pressure, volume, temperature, and number of moles. And because it's got pressure in it, it's that kind of equation of state is known as a mechanical equation of state. From that, we derive an equation of state relating the internal energy, the volume, temperature, and number of moles, which is the corresponding thermal equation of state. Okay. Now, obviously, this kind of thing is very useful in chemistry, physical chemistry, and condensed matter physics, and any condensed matter physics that's applied to high energy physics. Okay. Next, we have a look at some examples of equation of state of some exotic and not so exotic systems. Now, what kind of systems have you seen so far? Ideal gas. A little bit boring, right? Actually, not totally boring, ideal gas, as we'll see, but relatively boring. There are some interesting systems out there starting with the ultra exotic system rubber band. All right. So I probably won't actually derive anything here, but I will just show you the equations of state and ask a couple of questions. I might leave it for the assignment. I need to still write the assignment. I don't want you to work too hard in the assignment, but it's such an interesting question because it's a completely different type of system than you've ever seen before, and so it really tests your knowledge of the principles that you've learned, because you would be applying the principles to an entirely different system for which you have no intuition. All your intuition's wrong. Right? So it sounds really, and you learn something about rubber bands that you never knew before. All right. Photon gas. Anyone heard of what a photon gas is? Does anyone, do you know where you can find a photon gas in your kitchen?
Flame.
No. Microwave oven, right. So, unfortunately in EM1 we didn't get to standing waves of electromagnetic standing waves, but in your microwave oven, that's what happens. The microwave oven sets up standing waves, electromagnetic standing waves. The classical view is that the waves are, that the light is waves, but if you quantize it, then the particles, if you look at it from a quantized quantum point of view, then the particles are photons, and so your microwave oven contains a photon gas. So we'll have a look at the equations of state of a photon gas for your microwave oven, and we'll derive the fundamental relation, I think. Maybe just a brief qualitative introduction to magnetic systems, just 5 minutes. I just want to mention a couple of things, mainly because we look at magnetic systems are very important in thermodynamic theory and in statistical mechanics, because there are many exactly solvable models of magnetic systems, and it's one of the testing grounds of statistical mechanics and thermodynamics, and of course, it's very important physically. There are several labs, experimental labs at Nagoya University doing experiments with magnetic systems, such as M-Lab, over there, Professor Sato's lab, really interesting stuff, and Professor Ito's lab, I-Lab, on the 3rd floor in the same building. Very, very interesting experiments. I'd really encourage you to have a look at what these labs are doing. I-Lab, M-Lab, these are experimental labs. Have a look at Professor Widder's lab, which is just there's a building just across there. L-Lab. They also use magnetic resonance, do magnetic resonance experiments in superfluids. And so they're all doing very interesting stuff. I'm particularly impressed with I-Lab. What they're doing is really, really interesting experimental stuff, right? And I heard that you've already written down your choice for...
It's just a poll.
Yeah, just a poll.
Yeah.
I would really strongly recommend you have a look at what these experimental labs are doing, I-Lab especially, all right? And that's the one that I like. Professor Sato would probably think that M-Lab's pretty good. I'll have a look at that as well, right? And L-Lab, Professor Wada's lab. The thing is, you can't even begin to imagine what some of these people are doing because you've only just started 3rd year physics. And by the end of 3rd year physics, you will be able to tell you'll be able to understand a little bit in some way what these labs are doing. Right? The stuff that, what we're doing in physics is kind of just like learning to spell. Right? Just all the basic stuff. Okay? So we've got a lot of work to do and just to begin to understand what these people are doing. But yeah, I'd have a very good look, and you can talk to me about what the labs are doing as well. We'll derive the fundamental relation for the one component ideal gas. Callen actually calls it a simple ideal gas. You can read what he means by simple. And then we'll use that we'll actually construct the fundamental relation from the equations of state, the ideal gas. And then what we'll do, in fact, I think what you're going to do in an assignment is you're going to check out how the entropy changes in two different situations. You have a composite system and it's divided into two, and there are ideal gases in each compartment and they're in thermal equilibrium. But the two different situations, you'll have identical particles in one experiment, and in the other experiment you have distinguishable particles. So in other words, in one experiment both chambers have indistinguishable particles, identical particles, and for the other experiment the chambers have identical particles. What did I say? The opposite, yeah, distinguishable particles. Okay, and when and suppose that the partition is taken away so that the gases in each chamber can mix. What's the change in entropy in each case? Okay, and what you'll find is that, except for trivial cases, there is a difference in the change in entropy. And the question is why. I'm just trying to understand that. So that's this bit here, all that bit there. And so we'll talk about what's called the entropy of mixing. And I think that I'll leave parts of this to the assignment, and so you can explore it in the assignment. The last thing, which I may or may not do today, is just very simple. Just looking at some second derivatives of, let's say, S of uv, second derivatives at constant mole number, and how many independent second derivatives are there? Well, there's d2u, d2s by du squared, d2s by du dv, d2s by dv squared. There are only three. And they're three different properties of matter. In fact, for some reason, there are six. I said there are six. I need to try to remember why I thought there were six, but that'll come up when I get to it. Anyway, there are only, each second derivative corresponds to a property of matter. But the thing is that they seem completely unrelated. Like thermal expansion, the expansion coefficient, and for example the heat capacity or compressibility. If you change the pressure, if you increase the pressure a little bit, how much does the volume change? A lot or a little bit? Does it have high compressibility or low compressibility? That is related to the heat capacity. So it's there are these almost seemingly, if you didn't know why this is so, because of the mathematical structure, you would think that this is some sort of magic, some sort of alchemy almost. But because of the underlying mathematics, you can understand why they're related. And so that's the topic there. If we don't do it today, we'll do it next week or whenever. It'll come up definitely in lecture 6 and 7, something like that. Okay, so let's begin. Why does the mathematical theory work? Now, I've picked this version of the theorem from Widder because he mentioned something that I've never seen before in any other maths book. And I've seen quite a few maths books. And what I want to first define is an idea of simply connected region. Have you heard of what a simply connected region is?
Yeah.
Okay, so how do you define a simply connected region?
You get the loop and
Let's say we've got a region, some region R. How do you? What's the definition of simply connected?
you can get points. You get a loop, and if you can what is called
Very good. Homotopy
into a point.
To a point. Yeah. It's homotopic to a point. Right. So okay. So you make a hole in this region. somehow, and you put a loop. Now, what if it's a three-dimensional region? And it's a surface. Or something, yeah, okay? So you put a loop, so this is supposed to be a loop around here, and there's a piece of string, okay? And then you pull the string down here, and make the loop smaller and smaller and smaller, and if the loop always remains inside this region, then and eventually disappears down this little hole, then this region is simply connected. What's an example of this failing? What if there's a hole in the middle there? If there's a hole in the middle there, then if I pull this string down, then I get stuck around this hole. Well, I have to move over this hole, and suddenly part of the string is not in the region. Okay, or I could have two separate regions like that. It's the same thing. So even the string would actually even start like this. Okay, obviously there's a technical definition, but after learning all the technical stuff and all the symbols and all the ideas in technical language, the intuition is exactly this. So you wouldn't gain anything by anything that we need at the moment by formulating this precisely. Right? That's it. Okay, so that's simply connected. So, theorem 1. Suppose we've got three functions and they're C1 functions. What does C1 mean?
Continuous.
Sorry?
Continuous one.
Continuous?
Differential ones.
Yes, their derivative is continuous. Their first derivative is continuous. Okay? So not only can you take the first derivative is continuous. So in other words, the functions, this is f of x, and this is x. They don't look like that. That's not an element of C1, because this is not differentiable at that point. Right. Now, suppose we have these three functions, p of x, y, z, q of x, y, z, r of x, y, z, in a simply connected region. Suppose p, q, r satisfy the following condition inside this region. So dq by dz equals dr by dy, dr by dx equals dp by dz, dp by dy equals dq by dx. It's kind of a cyclic permutation. Then there exists some function f of x, y, z in the region, which when differentiated gives the pqr's. So df by dx equals p, df by dy equals q, and df by dz equals r. So because, and because it gives p, and p must satisfy a derivative, it must be differentiable, p must be differentiable, f must be twice differentiable. So this here is the most general possible condition. Okay? So if f does not exist, it does not mean that you can look for a C3 function, because C3, the set of C3 functions is smaller than the set of C2 functions. There are C2 functions that are not C3. Okay.
It's some sort of, it's like a potential.
Yeah. So, and if you want to see the proof, you can see Widder, page 251. Theorem 2. Consider the line integral. Now, this is a line integral from some point in R3 to another point in R3. Point ABC to point XYZ, some general point. And the line integral is p dx plus q dy plus r dz, where these are the same pqr as above. And it's along any curve, gamma, joining the reference point. Any curve. So it's a line integral along the curve. Okay, okay, joining the two endpoints. Now, if PQR are C1 in the simply connected region, and they satisfy the same condition as before in that region, and gamma has to be piecewise smooth, so gamma can be like that. That's piecewise smooth. Okay. Right. Then the integral is independent of path, or independent of gamma, independent of the path. Right. Right. So you have seen this before in MP2. And also in MP1 with exact equations. So the application to physics is suppose PQR satisfy the conditions of the theorem, and suppose that PDX plus QDY plus RDZ equals 0. Right? Suppose that this equals 0. Then the first theorem tells us that there's some function f such that df by dx dx plus df by dy dy plus df by dz dz is 0 because df by dx is p, etc. But look at this. This is df by dx dx df plus df by dy dy plus df by dz dz. That's equal to the total derivative df, or total differential df. Right? And if df equals 0, it means f equals constant. Right? What that means is that, well, this thing, but by the way, this thing here is then called an exact differential equation, right? Which is what we looked at in MP1, except this is one more variable. And df is an exact differential. It's an exact differential because you can write it as, because df equals this. It's exact. And it's independent of path. The significance is then that the line integral that we had, integral along any path from an initial point to a final point of this integrand, then equals the integral of along that path of df, but then by the fundamental theorem of calculus, that's just f evaluated at the endpoints. So that means that the value of the integral depends only on the value of this function f evaluated at the endpoints. Okay. It doesn't matter how the system gets from the initial point to the final point. It just gets anyway, in any way, from the initial to the final point, and you know what the difference in f has to be. Yeah.
Professor, but didn't you say it's constant?
Sorry?
Didn't we say it's constant? F is constant.
df is constant. The f is constant.
So this is 0.
This was the case in which it's 0, right? But
Was
in that
that-
it's not 0.
So we went back to the general case.
Yeah. So the physical significance is that the value of a physical quantity given by the line integral does not depend on the process used to get from the initial to the final point. Instead, you evaluate another function at the end points. And that function is called a potential function. Okay? Now you have already seen several of these in mechanics and electromagnetism. Like potential energy, magnetic vector potential. Now what about in thermodynamics? In thermodynamics what we have is 1 on TdU plus P on TdV minus mu on TdM equals 0 if and only if ds equals 0. Okay. So at the maximum entropy, or minimum, but we're interested in maximum entropy, for an isolated system at equilibrium. Okay. For the thermodynamic potential, S of UVN. And TdS minus PdV plus mu dN equals 0, if and only if du equals 0 for an isolated system at equilibrium. For the thermodynamic potential U of SVN. All right. Now, since the value of the physical quantity given by the integral does not depend on the path taken to get to the final point from the initial point, the system, once it reaches the final point, has no memory of how it got there. No memory. Okay? The same is true because the variables that you need, the variables that specify that final point, are only UVN, not any other U's. Not what U was slightly, somewhere else. There is a reference point, but that's different. There is no you do not need any more variables. You only need U, V, and N that specifies that point, and that tells you what the value of the function is at that point. Only 3 variables, U, V, N. That means no memory and no hidden variables as well. Anyway, the same is true of the derivatives of the fundamental relation, basically the temperature minus P and mu. And so the value of these values of these functions depend uniquely on the value of the independent variables SVN or UVN. So these functions are called functions of state. They depend only on the state, the triple SVN or the triple UVN, not on any other variables. No hidden variables. Finally, these theorems also imply that, for example, d2s by du dv, so in other words, if you differentiate s first with respect to v and then with respect to u, you get the same result differentiating s first with respect to u, then with respect to v. In other words, the cross derivatives are equal. So that's because s is a potential. And so on for any pair of extensive variables and any thermodynamic potential. So basically a consequence of this, a useful consequence in thermodynamics, is that if you have a function, a fundamental relation, entropy or internal energy, or in fact any other thermodynamic potential, which we'll get to in a couple of weeks, the first derivatives of these, or the fundamental relations, must be what's called compatible. In other words, if you differentiate the equations of state, the different derivatives must be equal. Okay? So this leads to a practical method for obtaining a second equation of state given one equation of state. Okay?
Why must they be equal?
The first derivative, because the equation of state is the first derivative of the fundamental relation.
Okay.
And the second derivative must, the cross derivatives. Must be equal.
Oh, okay.
Cross derivatives of the fundamental relation must be equal.
Okay.
Yeah, that's what I'm saying. Okay. Yeah.
The condition for simply connected holds at any time.
Yeah, I've never heard of a thermodynamic system where the domain is not simply connected. I don't know how it would even occur. But just because I can't think of it doesn't mean it can't happen. The theorem says the region has to be, the domain has to be simply connected. So maybe there's some kind of system out there that where the domain is not simply connected. I don't know. Some combination of U, V, and N where the system can't go. There's a hole. And then all this falls down.
Maybe like if there's a barrier.
No, that's different. That still restricts. The volume means the volume is restricted to some finite region. That's different. So yeah, I mean that's why just to get your imagination working, and just keep in mind when you're doing research, maybe somebody somewhere will find an experiment on a thermodynamic system where some values in the domain are excluded. And I'll guarantee you one thing, there's probably no other statistical physics course in the world that actually mentions that. Maybe because there's some trivial reason why it can't be. But maybe there is a thermodynamic system out there. So just have a look. Just keep it in mind, back in mind. One last point that I want to make is this. So we've also seen that in a quasi-static process between two states, I and F, where these two states are separated, these two states are very close together in a thermodynamic sense for a particular system. Whatever close together means for that system. The heat absorbed is an imperfect differential, d slash the dq, and the work, quasi-static work, is dw, and it depends on the path taken from the initial point to the final point. So these quantities are path dependent: the work done and the heat absorbed. In fact, the heat absorbed, the quasi-static quantities, dq and dw, depend on the process in such a way that the sum of dq and dw is equal to the differential, the perfect differential of the internal energy. Because the internal energy is path independent. And this is the first law of thermodynamics. So it's kind of saying, yes, certainly conservation of energy, but I think it's more interesting than just conservation of energy, because it's saying that Q and W you can go in any path and you get the same du, get different dq's and dw's but the same du. You don't have to go quasi-statically between these 2 points from I to F. You don't have to go quasi-statically. You can go fast. It doesn't matter how you get from the initial state to the final state. In the final state means a particular value of S, B, and N.
At equilibrium.
Yeah, at equilibrium, right. So you lock in the values of S, B, and N, and you let if you go fast, the system's a mess, for example, it's a gas or liquid, right? And you just lock it in, let it achieve equilibrium again, and you're guaranteed to get the du that is exactly the same as if you'd taken a quasi-static path between them. But all the other, the Q's and W's will be completely different. Now back to this, a mathematical point. In general, if you have an imperfect differential dr, and it's a sum of mdx plus mdy plus mdu, and the way to solve this is to seek an integrating factor, lambda, the function of all the variables that you need. In this case, it's x, y, and u, such that lambda times dr is equal to a perfect differential. That's the idea of an integrating factor. If you go back to MP1 and remember, like in lecture 3, we did exact equations. We did exactly this. So this is precisely what's happening in thermodynamics. So here is an imperfect differential multiplied by an integrating factor, and you're looking to find a lambda that will make this product a perfect differential. So that's lambda times all that. Then what's the condition that the coefficients, what's the coefficient, what's the condition that that the lambda m, lambda n, and lambda p must satisfy? The conditions are that dz by dx has to equal that, dz by dy has to equal that, dz by du has to equal that. You have to be able to put that there has to be dz by dx, constant yu. That there has to be dz by dy. That there has to be dz by du. And if that's true, then you have the total differential. Well, there's a partial derivative there, a change in dz. What contributes to the change in z, infinitesimal change in z, it's the infinitesimal change in the x direction, plus in the y direction, plus in the z direction. If you can write that, then you have the total derivative. And it turns out, I'm not going to go into any details, well, actually, and the second theorem, or I think it was, tells us what the conditions are on these. d lambda n by dy has to equal d lambda n by dx, etc. So in other words, you have second derivatives of z equal. But I'm not going to go into the details, but I just want to tell you that this gives enough equations to identify the integrating factor. And in standard thermodynamic theory, and even in axiomatic thermodynamic theory, it's a fairly short derivation to show that the integrating factor is 1 over the temperature. So, and any imperfect differential that we're interested in is dq. And so you multiply dq by 1 on t, and you get a perfect differential. Yes.
Why do we have those conditions?
These ones?
Yeah.
That's from. That's that.
Oh, but why can we apply this? Because in that it was like we said that it must satisfy that, right?
Because we're looking for an integrating factor that makes the product of the imperfect differential and the integrating factor a total differential. And we know what conditions these must have, these coefficients must have, if that's a total differential. And so this is just the outline of the steps for proving that that is an integrating, 1 on t is an integrating factor for dq that gives you ds. This is from axiomatic thermodynamics, but also from the standard thermodynamic theory. There's two different ways of doing it. There's no way that I want you to be able to do this. You don't need to be able to do this or show this. But I just want to tell you that this is why ds equals 1 on t dq from a mathematical point of view. Okay? Yeah. So that's where absolute temperature comes from the axiomatic thermodynamics point of view. Not Carathéodory's derivation, which is what I told you in lecture 1, the one with the surfaces. This is the axiomatic view. All right. So that's that. So just a few minutes ago, I said that that the first derivatives of the fundamental relations must be compatible in the sense that we'll see in a minute. That gives us a practical method for finding a second equation of state if we have one equation of state. Obviously, that's a very useful thing to be able to do. So we're going to show this by example, and the example will be the van der Waals equation of state. And this was proposed in the early-ish 1800s, 1830, 1840, something like that, wasn't it? 1840, around about that. Maybe 1850. Someone can Google it and check it out. It's the first correction to the ideal gas law. Okay. So you remember that the ideal gas law is PV equals nRT. Well, if you divide through by the number of moles, you get P little v equals RT. Right? And what do we have here? We have P, and if I take the little v on this side, this is the ideal gas law. Little p is RT on little v. So what's this? This is the first correction. RT divided by little v minus b minus a on v squared. Right. Can anyone guess what this, what the denominator is here? What the meaning of the denominator is here?
Actual fraction of the body.
Yeah, it's the actual volume of the particles. Right. Any idea where this term here comes from?
Pressure, correction of pressure.
Very good. It's a correction. It's a pressure correction. Very good. Yeah. So there's a pressure correction. I don't want to go through the justification for it. You can read it for yourself. In fact, in SP2 we derived this in statistical mechanics in two different ways. So I'll just go.
So this is just an example.
Yeah, we're just doing an example, and I just wanted to explain what the van der Waals equation is, just so that you get a feel for it. So it's the first correction to the ideal gas law. And it turns out to be very rich in behavior. In fact, it predicts phase transitions. The ideal gas law has no phase transitions. But you just do the one correction, one little correction, the first correction, and you get phase transitions in your system. And that's what we look at in SP2. Okay, we're going to look for another equation of state that involves the internal energy. So, since internal energy is a variable, which picture are we looking at? Which representation? Entropy or energy?
Entropy.
The entropy representation. How do you know? Because one of the variables is the energy. Right? So, the first step in a systematic way of solving thermodynamic problems is work out which representation you're in. So now that we've identified the formal structure of thermodynamics, now that we've identified the representation, there's a word missing there. The formal structure of thermodynamics will guide the calculation. Okay? So, what do we have? We have the entropy representation. So we need to rewrite the van der Waals equation of state in terms of the entropy representation. So how do we write it to make it conform to the entropy representation? On the left-hand side, we want the intensive parameter, the entropic intensive parameter that involves the pressure. It's P over T. Okay, so it's P over T. So we write P over T on the left-hand side. And so you need to divide through that term there by T. And what we want is the other entropic intensive parameter, 1 on T. Right? And it's got to be some function of the molar internal energy and the molar volume, because we're keeping the number of moles constant. So, the first law in molar form is ds is 1 on TdU plus P on TdV, because it's entropy representation. And ds must be an exact differential. The theorem tells us that in order for ds to be an exact differential, the derivative of this with respect to v must equal the derivative of this with respect to u. The cross derivatives. That must be true. And which means that really what it's saying is that the cross derivatives of the entropy, molar entropy, must be equal. That's what it's saying. Okay. So I'm kind of working backwards like that. Or not necessarily working backwards. Okay? So we know we have this. But this has a special structure. I want to show you what can we say about, suppose we have the same thing in general, so we have a function of x and y, d by dx of that function there at constant y, and that equals d by dy at constant f of xy. So the derivative, this is the derivative in the x direction, and it's at constant y, and derivative in the y direction at constant x, and they're equal. They're equal.
The function is symmetric in a way.
And then you can exchange x and y.
Okay, so yeah, you can exchange x and y, but that's not really saying anything.
As in, you don't need to.
What the question is, which combination of x and y is f a function of? This is saying, in fact, that here, the argument that goes in the function f, there's some combination of x and y.
X squared plus y squared?
How did you get that?
It's
It's wrong.
symmetric.
I mean, it could be x plus y.
So you just, yeah,
X, Y.
X plus y,
x plus y,
x
okay.
minus y.
Yeah, okay. Let's see what the math tells us. So what I'll do is define variables. Xi is x plus y e to x minus y. So I'm going to change variables. So f is a function of x of xi eta and y of xi eta. So df by dx at constant y is then, by chain rule, df by dxi by dx plus df by d eta by dx. And df by dxi, so dxi by dx is just 1. And d eta by dx is just 1, so it's df by dxi plus df by d eta. And then df by dy, now this d eta by dy here gives a minus 1. Yeah, there, right? Yeah. And so now, what we know is that that equals that. Right? So if that equals that, what I'm going to do is subtract this minus that. Right? This minus that. So df by dxi goes away. And we got 2 df by d eta equals 0.
So it's a function of x plus y.
Right, so f of xi eta has no explicit dependence on eta. It's a constant, f is constant in eta. Constant function of eta. Now, it does not depend on eta. No explicit dependence. So that means it must be just f of xi, which is f of x plus y.
And that's a general for anything that applies.
But how could we guess x plus y? Like, how could we guess?
So that depends on this. You might try, will this work? You can try it. You said a few other things, s squared plus y squared, x to the n plus y to the n, or whatever. Okay? Any constant times that, obviously. Try it, see if it works. I'm not going to tell you. I don't know the answer off the top of my head.
So it's
but certainly, f of, yes, try it now here. Certainly, f of x plus y works. Now, we want to try to find the second equation of state. So what do we got? The pressure, oops, we got a compatibility relation. Yeah?
How could we tell that that the function is of a particular form? Like,
because this is special. This here, the fact that the slopes in these two different directions are equal is something special. All right. So the compatibility condition for the van der Waals equation is that the derivative of the entropic intensive parameters must be equal. So d by dv of that equals d by du of that. And we know that p on t is that, so we put it in. There, that equals that. So now look at the left-hand side. So what's d by du of that when v is held constant? 0. R is a constant, b is a constant, v is held constant, and it's independent of u anyway. So that's 0. How about this one? D by this is d by d.
du.
Small u.
U is it?
Yes, because below is
It's supposed to be d by dv, isn't it? Oh yeah, it's here. Yes, d by du of that. Yes, it's the left hand side. Yeah, d by du of that. And that must equal the right hand side. D by dv of 1 on t. So that must equal that. So just multiply, put v squared on this side. So we've got minus v squared multiplying that there. And we've got d by dv there, and minus v squared there. And then, last thing, this is a typical step that you see in thermo. D by dv of 1 on v equals minus 1 on v squared. So just writing it as a relation between differentials, d1 on v equals minus dv on v squared, or here we have d1 on v, you put minus dv on v squared in there, gives minus v squared there. That shows why that is true. And then here, I just put the a under here, like that. Okay? So, that's that. Now, that's just explaining that step there. That's that. So we get to here. And now what do we do? What do you think we're going to do here?
Chain.
Nope. What's held constant there?
oh, so we use the thing that we just did.
Exactly. This is the slope of 1 on t in the direction of u on a.
Yeah.
This is the slope of the same function in the direction of 1 on v. So so the trick was to get the same function here and here.
Yeah.
And that's the trick.
You can express
Yeah.
1 by t as a function of the sum of u by a.
Exactly. So 1 on t must be a function of u on a plus 1 on v. There it is. So 1 on t must be a function of 1 on v plus u on a. Okay. And which is the same as, just to sort of, I want to isolate the internal energy just for niceness. 1 on a function f of 1 on v plus u on a is also, but is equal to f of 1 on a times that. And if I just define another, trivially define another function where I just scale the 1 on a away, this is a function of u plus a on v. So 1 on t is a function of u plus a on v. So that's just, yeah, all we need is some functional form for 1 on t. Just some functional form. And, okay, that's as good, that's as much as we can do in terms of uniqueness. As in terms of, that's the information that we're given. So from the information that we're given, we know that 1 on t must be some function of u plus a on v. Which one do we choose? What function do we choose? Well, obviously, there's no mathematical uniqueness. Okay? But what we can do is argue for the simplest function based on what we know. So, the ideal gas, the molar, you know that U equals N times the NCRT for the ideal gas. So that means little u on CR equals T, which means this is little u, which means 1 on T is C big R on little u. This is for an ideal gas. And if you look at well, the van der Waals equation of state is a correction to the ideal gas. So we would expect whatever function this is to be not very far away from the ideal gas law. It should be close to this. That's a physical argument. It should be close to that. So we would replace u in here. We know that 1 on t in the van der Waals picture has to be a function of u plus av, not just of u. So what's the simplest possible thing? What's the simplest way of adding a correction to this that's consistent with the what we worked out mathematically? Just replace u with u plus a on v. Physical argument of what must be the form of 1 on t. The last part is physical. Okay. And so there it is. So we try that, and this is going to be correct. So now, even though mathematically this is not unique, from the physics, in fact, mathematically it is unique, but it's a much bigger mathematical picture than this small set of facts that are used to derive this. What happens in physics is that this is a typical situation. So, and it drives mathematicians nuts. Because this is going to be the correct, the unique, mathematically unique, correct equation of state that we want. The reason is that the proper derivation of the van der Waals equation of state has already thrown away higher derivatives and more complicated forms. It has thrown away the complicated forms, the high derivatives of a Taylor expansion, and kept only the first term. It's already simplified.
Where?
If you derive the physicist would tell you, if you derive van der Waals equation properly, you have thrown out all the more complicated terms in the derivation if you derive properly.
Okay.
Right? So by the same argument, we keep the simplest term here, not u plus a on v squared, right?
Yeah.
Or u plus a on v cubed, or u plus a on v plus u plus a on v squared. Right? Technically, that also fits this. Right? But we keep the simplest form because in the proper derivation of the van der Waals equation of state, you've kept only the simplest form. And that will turn out to be a mathematically correct argument if we filled in the details, like 10 pages of details. So the physicist has done it intuitively, using the argument that it must be so. It must be so, because if you derive the van der Waals equation properly, you've already thrown away all the harder terms, the more complicated looking terms. So I'm not going to do that explicitly. I know it's true. Right? But the mathematician won't believe it and will want 10 more pages to actually derive the van der Waals equation properly and actually see it happen. So this is a typical physical argument. Right? Anyway, we've achieved our goal. This is the correct equation. Okay?
But whether it's correct or not is verified by experiment.
Yes. Yeah. But also, if you derive the van der Waals equation properly, and in fact, what you can do now that we have two equations of state, you substitute it into the first law, and you would get this entropy function. It's u plus a on v to the power of c, which is essentially all you have to do is everywhere where you see v, molar volume in the original, you substitute v minus b. Everywhere where you see u, you substitute u plus a on v. And so it's a two-line argument. You do not have to do 2 pages of calculation to rederive the entropy. But you have to know the fundamental relation for the ideal gas, which we haven't done yet. We're going to do it in about a minute. Okay? So from the fundamental relation of the ideal gas, you can write this down in 2 lines. Okay? You do not have to do a pile of work. And it's a valid argument. Okay? All right. So it really works. Which one is it? Okay, good. So let's have a look at some examples of exotic and not so exotic systems. Rubber band. So what's a rubber band? Lackey band. We call them lackey bands. So basically it's a bundle of long polymer molecules that fold and unfold as you stretch or release the rubber band. So the kind of like looks like this. Now, a link, a link, a link, a link, and then a link, and then this sort of goes back on itself, and then maybe forward a bit, back on itself, or maybe back this way, then forward a bit, back, and then forward, etc. like that. And then when you pull the elastic band apart, this kind of unzips. So it goes, it gets longer because these folded bits unfold, sort of unzip, like that, like that. That's how it works. How would you write down the thermodynamics or the equations for the elastic band? Well, the thermodynamics, the structure of thermodynamics guides the construction of the model, plus experimental input. So, what are the variables? The macroscopic thermodynamic parameters that we're interested in. We've got the length. There's also like an unstretched length, L0. There's a tension, that's supposed to be a tau. Sometimes I write tau like that, like a Japanese ten. Maybe I should write, I don't know, sometimes I do that, sometimes I do that. Sometimes I write that and it's awful because it looks like an R. So tension, temperature T, internal energy U. Now the tension plays the role of minus P and the length plays the role of the volume. And there are 3 experimental facts, and these will surprise you. For a fixed length, the tension increases as the temperature increases. So if you fix the length and you heat up a little bit, in fact the tension increases.
I think that makes some sense. Yes. Because it's
They pull on each
they
other.
want to pull. Because the molecules like want to move away. So
Well, maybe it tries to shrivel up.
that would probably depend on where you heat it from. Maybe.
Have you ever put a piece of plastic in an oven, shrivels up, it shrinks. It shrinks. The stretched length is proportional to the tension. Okay, that sounds, the delta L, that sounds reasonable. And now this is the one that is the killer. The internal energy is independent of the length. Okay. There's a problem in Callen that addresses this 3.7.
So this U is not an extensive quantity.
Oh, it is.
It is, but it
depends
doesn't
what-
depend on L. So lambda L doesn't make a difference.
Yeah.
for one piece of rubber band.
Okay, so and now there's no uniqueness here, but you just want to model. A simple equation of state consistent with number 2 is that U equals some constant times the unstretched length times temperature. So that's kind of that's number consistent with number. I think it's consistent with number 3.
Yeah.
Yeah, number 3.
No.
Yeah, consistent with number 3. Consistent with 1 and 2 is that the tension equals a constant times the temperature times if the length is between some L0 and L1 and you don't stretch it beyond its plastic limit, then that's L minus L0 divided by L1 minus L0. So it's like the proportion of the length that you're going to stretch it. That's the tension. But also it's proportional to T. And there's an exercise that I might set for the assignment. Why must, or I might answer it now, why must the tension be proportional, why must it be a linear function of the tension?
Units.
But then you have B, and B can be any, can have its own units.
B is just a constant that has whatever units have to be.
The units argument.
So it's not the unit argument, no. It's an argument from thermodynamics, from some conditions that we've already seen.
Which is the pressure.
Yeah, it's like the pressure.
It's like the
yeah.
pressure.
Yeah.
So that is U by
Is it like the ideal gas equation?
No. The equation of state, the fundamental relation is completely bizarre. Anyway, I might set this in the assignment, and you can really think about it. Okay. And I'll give you a clue. We've done it. It's in what we did. We've done already.
Maybe it's related to the slope. I don't know.
Or because we removed the higher terms?
No. Okay. So what I'm saying is that thermodynamics limits. So you want to build a thermodynamic model, and the theory limits or tells you the boundaries or the limitations, or basically guides you what the equations have to look like. Okay, but that's all I want to say about that. And maybe I'll give it in the assignment to actually solve the last part, which is just essentially, I think, problem 3.72 in Callen. Okay, photon gas. If the walls of an empty black box, empty in the sense of, well, it's never really empty. It has no gaps in its walls, and it may be a tiny hole, out of which light comes, and which is the black body radiation. Anyway, if the walls are at a temperature T, then the electromagnetic radiation fills the box because the box absorbs because the walls absorb and re-radiate light. The electromagnetic field inside the box eventually reaches equilibrium with the walls itself. And that field is the photon gas. So it's a gas of photons that reaches equilibrium with the walls. See, and in Callen there's a question where, imagine if the universe is just one giant container, and the cosmic background radiation has reached equilibrium with all the matter in the universe. What would be the energy of the universe? There's an example. So the energy is given by the Stefan-Boltzmann law, which we just quote. It's, okay, let's say it's experimental. So it's proportional to the volume and proportional to the temperature to the fourth power. And B is a constant with the appropriate units. And the pressure is U on 3V. Again, let's say it's a given. So first of all, we are in the entropy representation because the energy is a variable in the equation of state. And notice that the number of moles is absent. Can anyone guess why the number of moles is not a variable in a photon gas or electromagnetic field?
The wave nature.
So,
I mean, you can't really tell exactly.
Excellent. They're not just absorbed and emitted, they're being absorbed and emitted, absorbed by the walls and emitted. The thing is the number changes. So the wall absorbs one photon and you might re-emit 2 or 3 at lower frequencies. Yeah. So the walls are absorbing photons all the time and re-emitting them, maybe several, or absorbing 2, re-emitting 1. The number of, you cannot control the number of photons in a photon gas. It's not a controllable variable.
But wouldn't it depend on the material, maybe, of the thing? Like the rate at which, or which frequencies are given out?
Not in a black body. Okay. So, so we have 2 equations of state. And we only have 2 variables. The entropy must be a function of only 2 variables. And so we just substitute into the Euler relation, putting n equal to, ignoring n. So the Euler relation in the entropy representation is S equals 1 on Tu plus P on Tv. So that just means that you have to you have to put this equation into the correct form, 1 on T equals something. And this equation, oh, you have to get another equation involving P, and it has to be P on T. You have to get it from somewhere. Right? So, put 1 on, get 1 on, okay, so 1 on T is just going to be, so 1 on T to the 4 is BV on U. So that 1 on T is B to the quarter, V to the quarter on U to the quarter. Right? So that's that trivial exercise. And P on T is then P times 1 on T. So that's just P times, so that's just U on 3V times that. And then you substitute into the Euler equation, and so the entropy of the photon gas is this plus that, and obviously you just simplify. You eventually get 4 on 3, b to the quarter, u to the 3/4, v to the 1/4. And just check, is it homogeneous order 1? Put lambda u in there, lambda v in there, you get lambda to the 3/4, lambda to the 1/4, so that's lambda to the 1. Yes, it scales properly, the entropy scales properly. Yes, it does. Okay, so that's the entropy function. And from this, you can, I mean, the theory already tells us that if you differentiate this with respect to u, you'll get the correct equation of state. Differentiate this with respect to v, you'll get the correct mechanical equation of state. Oh, and by the way, the photon gas exerts a pressure. Yeah. Okay. So in principle, you can go, if you had a sail that's big enough and I guess light enough, you can go sailing on the solar wind.
In space. Or in the micro.
In space.
In space. Or in the micro.
You're actually designing something like that, isn't it?
Yeah.
I don't know.
You're actually designing something like that.
Using butterfly wing designers. Yeah.
Okay, I don't want to spend too much about magnetic systems. I just want to say that the total magnetic dipole moment, M, magnetic dipole moment, so if you remember that magnetic materials are basically the dominant the dominant contribution is from the dipole moments and from last year's M1 class. And basically an external magnetic field polarizes the material in the sense that it creates a total dipole moment. It makes the bar magnets, a dipole moment is essentially like a bar magnet with a north pole and a south pole. If you put a magnetic field through the spin system, for example, with dipole moments, it'll polarize it like this, and the magnetic, and it causes a magnetization to appear. M is a total dipole moment of the entire material. Now this corresponds to the volume that we've been looking at, except that for one thing, you cannot constrain the magnetization. You cannot stop the the dipole moments from aligning in a controlled way. You cannot. It's not like a volume that you can control, but you cannot control the magnetization by mechanical means.
So yeah. This would mean it's some sort of, it's not simply connected. Because it will be like you can't achieve the middle region if you.
But there's no region at all, because the magnetization, there is no mechanical way of changing the magnetization. The only way to change the magnetization is by the external magnetic field.
But you can't. Can it be done continuously, like a continuous transformation?
Yeah. The magnetic field, this is completely different. What I'm saying, the point is, the magnetization is an unconstrainable variable. So there are thermodynamic systems, and magnetic systems are a prime example, where you cannot, you have no control, no mechanical control over the magnetization. And yet it appears in the equations, the change in internal energy is basically the external field dotted with dn, or if it's parallel, then it's b times dn. So the thermodynamic equations end up having a magnetization in it, dn, instead of a dv, but you cannot control the way cannot control mechanically. You have to control the magnetic field. I'm not going to go through it. You don't have to know this or anything, but I'll just say that this is the Euler relation and Gibbs-Joule relation for that type of system. You can read it if you want. It's something that we'll need next semester, not really this semester. Okay, just before we have a break, I'll just we'll just look at one more example, and that's the one component ideal gas. And this is what Callen actually calls a simple ideal gas, because U is proportional to T. Anyway, equations of state, which you learnt in wherever, high school, whatever, just are given. PV equals nRT and U equals C nRT, where C is a positive constant. So N, big N, is a number of moles. R is a gas constant. It's not here, but N with the subscript A is Avogadro's number. And KB, which I shouldn't really, we won't use it. No one uses this as thermodynamics because this is a quantity that comes from statistical mechanics. Boltzmann's constant is 10 to the minus 23 joules per Kelvin times that quantity there, 1.38. But that's a very large number, and I mean a very small number, and that's because you're looking at quantities that are molecular in size. So this comes from a molecular picture of systems. So it's not thermodynamics, KB, Boltzmann. That's thermodynamics, the gas constant. This comes from statistical mechanics. Anyway, so equations of state are given. Again, the variables are U, the extensive variables are U, V, and N. So it means that we are in the entropy picture and we want to find the fundamental relation, which is the entropy function. And, oh, by the way, ideal gas just means non-interacting molecules or particles that are moderate temperature. For a moderate atomic ideal gas, this constant is 3 on 2. It can be lots of different things in reality. So we're in the entropy picture, so we write down, to begin with, we write down the equations of state in the entropy representation. So this is the entropic intrinsic intensive parameters. 1 on T, just rewrite 1 on T here, from here. And then we need P on T, and this time it's easy, it's just P on T is NR over V. And just use, it's easier actually to use the molar variables here. In fact, there's one equation of state that's missing. That's the one for the chemical, for the chemical potential, involving the chemical potential. One equation of state missing. Right. Now, so we have 2 equations of state. So we either use the Gibbs-Joule relation to get the 3rd equation of state and substitute into the Euler relation, or you integrate the first law in molar form. Method 1 would have us do this. Here is the Gibbs-Joule relation. It relates the intensive parameters, the differentials of intensive parameters in the entropy representation. That's d mu on T is little u d1 on T plus little v dp on T. And as I said, we need that one more equation of state involving the chemical potential. So what's d1 on T? So 1 on T is is that. So d1 on T is minus CR on u squared. And dp on T, we need dp on, we have to put dp on T in there.
Wouldn't it be there du?
Sorry?
Du.
Oh, du, yes. Right. And dp on T is minus R on V squared dV. So therefore, d mu on T equals minus CR U cancels one of the factors in the denominator, so CR on U, du, plus, it's going to be minus R on V, dV. Okay. And then integrate both sides integrate this side from mu naught on T, like an initial reference value to an arbitrary value, or d on T, g mu on T. And here we're going to integrate this bit in terms of, with respect to, that's going to be du from an initial state to an arbitrary state, minus R dV integrated from the reference state to the final state. So here we got
over V.
What have I done? Over V, yeah.
Wait, over V.
Over V, yes. That's really important. So that's mu on T minus mu on T naught equals minus CR ln U on U naught minus R ln V on V naught. And now just replace the number of moles in, put it back in. So it's ln big. That's little. That's supposed to be a little u. So it's big U on big N, and that's little u naught. So it's big U naught on N naught, and minus R ln big V on N naught on V naught. And so we have, so now the order relation. So anyone who has to go, some people have got Japanese. Yeah. The order relation. In the entropy representation, there's a minus sign here before the mu on T there. Don't forget that. So we know what mu on T is. We know P on T, we know 1 on T. Put them in. So 1 on T is R on N U times U, that cancels. R on N V on V, that cancels. And then we got the minus mu on T. So this minus cancels, get pluses. N times C times R. There's the log term, plus N times R times that log term, minus N times that constant term, mu on T, reference. And now just combine. So there's CRN plus RN, so that's C plus 1 NR. And then here, we'd like to combine these logs. So if there's a C, if I put this that to the power of C, okay, then we got NR times that log plus NR times that log. So the sum of two logs is just the log of the product of the arguments. So that's U on U naught, N naught on N times N naught on N times V on V naught. And then there's that other term. So, and the final result, so combining those logs, you got NR ln U on U naught to the power of C, V on V naught, and then you got and n naught on n power of c there times n naught on n. So it's n naught on n to the power of c plus 1. You've got c plus 1 in the exponent. Plus, and then you've got that term and that term, but you just go plus n times s naught. You see there's a n there and an n there, so it's properly extensive. Okay.
Yeah.
That's okay, it's properly extensive, but you just call that big S naught, just the reference value for the entropy. Okay. And S naught is just C plus 1 R minus mu on T naught, the reference value for the chemical potential divided by the temperature. We actually don't know what S naught is. We don't know, it's all relative to whatever reference value that is, but it's really entropy differences that matter. It's just like a potential in mechanics. It turns out that with statistical mechanics, you can work out what S naught is explicitly in terms of fundamental constants, H bar, M, and and this is properly extensive. Let's just check that it's properly extensive. First of all, what can go wrong? Well, first of all, you put in lambda n there. Obviously, the lambda comes out the front, so that's no problem. And you have to make sure that in here, all the lambdas cancel out. So you put lambda u in there, and lambda v there, and lambda n there. So you have lambda to the c times lambda, so it's lambda to the c plus 1. And you have lambda, 1 on lambda to the c plus 1 there, coming from there. And so the lambdas all cancel out. And so there's no problem with the argument of the log. Okay? So the entropy we find is properly extensive. Okay? If we'd used, okay, that's that. If we'd used the method of just integrating the molar, you don't need the chemical potential equation of state if you do this, and so the whole result is slightly shorter. We'll just go through it because it's very short. So ds is 1 on TD. Now these are all molar quantities now. ds equals 1 on TdU plus P on TdV. And we just put in what we know, CR du on U plus R du on V. Integrate both sides. Now the left-hand side is integrated from a reference entropy S naught to S. The right-hand side exactly as before. And so we have S minus S naught. I've got S naught hat here to make it distinguishable from the previous one. CR ln U on U naught plus R ln V on V naught. These are all molar quantities. Replace the number of moles into the equations. Simplify, and you get exactly the same thing, except that you don't have as much detail for the reference value for the entropy. Slightly, the reference value is still a reference value, but it's not. It doesn't contain the gas constant. It doesn't matter. It's just a reference value. Okay, so that's a much shorter way of doing it. Okay, and what we'll do now is just have a 10-minute break. So we've just worked out, the fundamental relation for an ideal gas, and then there's the idea that suppose you have an isolated system, an isolated container, if you like, rigid, adiabatic and impermeable, so it's isolated. And let's say you have N1 moles of one species of gas and N2 moles of another one, N3 moles of another one, So you have several ideal gases in the same container, in the same volume V. And they're all in equilibrium because we're talking about equilibrium thermodynamics. What would be the total entropy, do you think, of the gas mixture in there?
Some of the
It seems reasonable that it would be S1 plus S2 plus, or it's a sum of the entropies. Why does it seem reasonal?
They're independent of each other.
Yes, because now suddenly we go into the microscopic view and we imagine that the molecules do not interact with each other. They do not restrict each other in any way. Okay, so they do not. So the fact that the molecules of one gas are there does not stop the other gas going into the same space, sort of thing. There's just a mixture of ideal gases. So we expect that the total entropies are some of the individual entropies in this situation. Yeah. Yeah. So that's called Gibbs theorem. I mean, Gibbs came up with this. In fact, oh wait, I'll say more about that. All right. Now, a slightly different situation. In fact, a greatly different situation. Suppose we have this situation here, and this here is a diathermal partition. Diathermal means it lets heat through. So you have it only lets heat through, but no particles, and it is fixed and impermeable. And I want to consider two different situations. Two situations. One, you have indistinguishable particles, or identical particles. In both chambers, if you like. In other words, the particles here are the same as the particles there, and they're in thermal equilibrium. And the other case is distinguishable particles. In both, and they're in thermal equilibrium. Each chamber, each subsystem is in, subsystems are in thermal equilibrium with each other. Right, so what are the equations that we know in case, let's say case 2, we know that there are N1 moles in subsystem 1 and N2 moles in subsystem, in the right hand one that says 1 and that's 2. And N equals N1 plus N2. And we know V1 and V2, and so V equals V1 plus V2. And okay, and we know the temperature T. Therefore, U1 equals U2 because the internal energy is proportional to. It only depends on the temperature for an ideal gas. If the temperature there is the same. Oh no, there's a number of moles. There's a number of moles. U1 is CnNC T, U2 N1, U2 equals CN2 RT. That's what we know, and therefore U equals U1 plus U2. So we know that. So what we do, and so the total entropy for, let's say, the distinguishable case, and I'm going to say initial here for a particular reason, is S1 initial plus S2 initial, the distinguishable case, and where it's the entropy in there plus the entropy in there, because the entropy, just add the entropy. Okay? Add it to quantity. Okay, that's that. And what I'm going to do is I'm going to take this partition away so that now the particles can move through the entire box. Okay? And we allow equilibrium to re-establish itself. And we ask, what is the S total distinguishable final? Equals da 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 da. And we ask, what is the change in energy for in the distinguishable case? Okay? And then we do exactly the same thing. We want delta S total for the identical particle case. Okay? And we want to compare these two. Right? And what you will find is that this here. This is from an assignment question from last year, which will certainly appear this year, either in next week's assignment or the one after. I'm not sure yet. You get that depending on what can be different. You can put this partition all the way across here and make this subsystem have 0 volume, or you can make subsystem 2 have 0 volume, or you can have any distribution of volumes in between, as long as V1 plus V2 equals V. You can also have any numbers of moles. Okay. And so, depending on the initial density, the difference between the change in entropy in the distinguishable case and the indistinguishable case is between 0 and nr log 2. It's the maximum possible difference is nr log 2. Okay. So, I mean, even though the initial conditions are the same in the distinguishable and indistinguishable case. Okay. So there's something about the fact that indistinguishability or distinguishability that gives an extra nr log 2 maximum of entropy change in this situation. What is it? Why does it happen?
Well, the particles have more room, right? If you open another volume, they have more room per particle. So I guess if we think of entropy as a measure of disorder, then there can be more disorder.
Okay. In fact, what you'll find is that in the indistinguishable case, if the initial volume is split exactly in half, so V1 equals V2, in the indistinguishable case, there is no change in entropy. Delta S indistinguishable equals 0. So you take the wall away,
Yeah.
And now the particles can move through the whole region, and yet delta S is 0. That's what you find. You will find this because you'll do the calculation.
From like first year physics, it makes sense.
So
like,
what?
Like before, we learned that entropy is like a measure of randomness.
Did I say that?
No, I mean, the last year we learned that. So with that, it would make perfect sense.
It's like it's like a voodoo doll.
Yeah. It's still like the intuition behind entropy is still slightly difficult.
Of course, naturally.
Because even in our class, we didn't really define entropy like properly, like.
Not yet. No. You'll have a very good handle of what entropy is by the end of this course. But we've got to take one step at a time. Still, that's not going to help you. Actually, it's the thermodynamics is full of surprises. It's a very difficult subject.
Oh, is it?
So why is this extra NR log 2 factor there for distinguishable particles?
Is it because if you put the n inside, then it's 2 to the power of n. So it's like the number of like almost states or something or ways, and then it's like a permutation.
Yeah, it's good. Yeah, very good. But why is it that you have it for distinguishable but not indistinguishable?
Because indistinguishable, the swap wouldn't change the state because they're the same. Like it wouldn't represent a different state. But for distinguishable particles, if you swap them, it's a different state.
So there are two states that are there. It's either there or there. And then if you swap, it depends on the number of particles that are there, because you can either swap them all, which would be 2 to the n, maybe.
So, yeah, like something like that.
That sounds pretty good.
But then like using what you've learned right now, it's really hard.
Yeah.
So,
Yeah, it's
without
very,
calculation.
It would seem mysterious from what we've learned.
Yeah.
But we're going to learn something more in the next minute, in about a minute. But that's from the. This is still going to be within thermodynamics. The argument you gave is a statistical mechanical argument. Okay, so you're going to get this question here, or this question here, in an assignment coming soon, either the next one or the one after. This is actual questions. So you're going to have to actually work this out. Okay.
Is it related to some sort of isothermal process?
No. Okay, you can read that bit for yourself. I just want to mention that some people call what I just said the Gibbs paradox, but that's not what Gibbs paradox is. Right? What we just saw is not a paradox. It's completely explicable. All right. We've just argued that if you have, in an isolated system, you have N1 moles of one ideal gas, N2 moles of another, N3 moles of another, and they're all in equilibrium with each other, then the entropy of the mixture is just a sum of the entropies, individual entropies. And if you actually just write down the ideal gas equation and use, it's very simple to derive this expression, where it just turns out to be more convenient to, instead of having internal energy here, instead of expressing the entropy in terms of internal energy, you change, using the equation of state, change variable to temperature, and it's very easy to derive this. Okay? So that's just what you just told me. This is just the sum of the individual entropies of the gases that make up the mixture, and they're all in the same volume, they're all in equilibrium in the same region of space. That's that. Now, if you manipulate this a little bit, you can get to this. This is exactly the same thing, equation 340. It's exactly the same. It's the sum of the entropies. But what you find, if you compare these two equations, here you've got, where is it? Here you've got sum of the J, Nj, Sj naught. Here you've got exactly the same thing to start off with. Here you've got sum of J, Nj, Cj, R log T on T naught. And here you've got exactly the same thing. But this term here, this last term here, has been expanded into these two terms here. Okay? So the challenge for you when you derive 340 from 339 is to just expand this last term to get that. Right? A little exercise. Okay? Now, look at the last term here. It's minus R, sum of a J, Nj log Nj over N, where N is the total number of moles of all the gases. This thing here, that last term there, is called the entropy of mixing. Entropy of mixing. And Callen's description of it, it represents the difference in entropies between that of a mixture of gases and that of a collection of separate gases, each at the same temperature and the same density as the original mixture. This is different, a different idea to putting all the gases into the same volume. Although, if you have them in separate volumes, if you have them in separate containers like this, what that's saying, if you have them in separate containers, they all have the same density and they're all at equal temperatures, but the volumes can be different. Okay, volumes can be different. And then what you could do, for example, is put all of this inside a big isolated container and take the lid off that one, take the lid off that one, take the lid off that one, and make them mix. And then you would have that first expression, the equation 3.39. But it turns out that if you look at the difference between the entropies of it will turn out that the difference in these entropies for arbitrary distribution of volumes will be the entropy of mixing, that last term in equation 340. And I'd like you to think about it and try to figure out why that is so.
Professor, you said before that if we have like the volumes are equal, then we'd have 0 as a difference.
For the, which case?
The
indistinguishable case, yeah.
Is it because basically the system is entirely symmetric, almost like this side is exactly the same as that side. So there's
something to do with symmetry. Yes. I mean, there's another completely different explanation where you bring in symmetry into it. That's a permutation symmetry.
So mixing would
as in if you interchange two, you would.
But no, you see, what you're talking about here now is a molecular interpretation. Okay. When you first start thinking about this, try to think only in terms of thermodynamics, thermodynamic arguments, because you don't know enough statistical mechanics yet. Although you're welcome to think about the molecular view and speculate a bit. Yeah. But so what I want you to try to understand is that last term, that's called the entropy of mixing term. And in fact, and this is and how it relates to that situation in that assignment question, which, as I said, a lot of people believe this is what's called the Gibbs paradox, and that's not correct. Okay, Gibbs paradox is actually something else. Now, about this, the last thing I want to say is Callen gives an excellent interpretation of Gibbs's theorem when you have a mixture of gases. Now, let's say you have this is on page 70. See, so you have like a container here, and initially you have two gases, the same number of moles of both gases in here. Just, I guess that's for argument's sake. It is it the same number of moles? We have two sliding walls, so V, N naught moles of a simple gas A, N naught moles of simple gas, ideal gas B. So you have the same number of moles, just for argument's sake, I suppose, of two gases in there. The region is called region beta, and it has a certain volume. And there's like a fixed wall here that lets through only particles of one type that are going to go through that way. It's permeable only to particles of one type. And what you're going to do? Oh, and there are two more like sliding walls that stay at the same distance apart. And these are this one is penetrable only to the gas of type the first one, type A, but not to type B. This middle partition is permeable to type B but not to type A, and the volume is going to be constant. So what happens is that this is a complete vacuum, and you slide this very, very slowly, quasi-statically, towards the right, so that this one filters out the type B particles, and the left-hand side here only contains type A particles. The middle bit contains A plus B, and this part contains type B particles, and this is still a vacuum. You slide it all the way across, and by design, these volumes match up. So eventually, in this half of the container, you've got entirely type A. In this half, you've got entirely type B particles. So here you had a mixture and a vacuum, and here you've separated the particles, type A and type B. So, now the temperature remains the same at all times here, and the energy, let's just have a look, the energy is a function only of the temperature and the mole number. The mole number is are the same. So that means that the final energy is equal to the initial energy of the system, so there's no change in internal energy. So that means that, see, if delta U equals 0, that means that Q equals W. The amount of, so delta U equals Q plus W. That is negative. That's 0, so Q equals W. And the Q is T delta S. There's a change in entropy in this system, in this process from there to there. It's equal to delta S. You multiply delta S by the temperature, which is constant. You get T delta S, and that must equal the work done in this process. T delta S equals the work done. Now, it turns out that, in fact, just using, you don't have to do this, but just using since the particle numbers of particles is changing, the equilibrium condition is equality of, for example, in mu for type A particles, equality of the chemical potential of type A particles in chamber A, alpha, and with the chemical potential of type A particles in chamber beta, and similarly for type B particles in chamber beta and chamber gamma. And from that, you can derive that means the pressures must be equal. The pressure in chamber alpha must equal the pressure in chamber gamma, and pressure in chamber beta, in fact, equals twice the pressure in chamber alpha, something that you just work out. Okay? Just take it as a given. Right? You can show it if you want. And that's at every point in the process. Because at every point, the systems are in equilibrium. Okay. Now, what's the total force on the moving walls? These moving walls. So for example, just looking at here, the force towards the right due to chamber alpha is the pressure P alpha, essentially, pressure per unit area. Yeah, P alpha to the right. And then chamber beta has a pressure beta, and it exerts a force to the left. So it's minus pressure beta. The total force on this part is P alpha minus P beta. And then on here, you've got the pressure gamma that way and 0 that way, because this is a complete vacuum. So the total force on this rigid body, that and that, is P alpha minus P beta plus P gamma. But from the equilibrium conditions, we found that P alpha equals P gamma and P beta equals 2P alpha, so that P alpha minus P beta is P alpha minus 2P alpha plus P gamma, but P gamma is P alpha. So it's P alpha minus 2P alpha plus P alpha, which is 0. So the total force, so the total force on this rigid body here, is 0 at every point in the motion. So what's the work done? 0 times delta x is 0, no work done. So T delta S must be 0.
So this must be 0.
So the change in entropy is 0. There's no change in entropy in this process.
And that's good.
So what it's saying is that the original mixture, the entropy of the original mixture is exactly equal to the sum of the entropies of the separated gases in the two separate regions. It's kind of nice, yeah. So this is a way of proving additivity of the entropy,
Yeah.
not just in two separate regions of space, but in the same region of space.
But then the additivity has to be done in a certain way, as in a
Quasi-static.
quasi-static.
Yeah, because if you don't have a quasi-static process, then you can't say that Q equals T delta S. This is only true
For
for quasi-static process. Yeah. Right. So that's that. All right. So I'll leave you with that, and the question that you can think about: why is there such a difference between distinguishable particles and indistinguishable particles, even within a purely in thermodynamics, a purely thermodynamic argument. This is a purely thermodynamic argument that you can derive from what we've done today, and try to explain it in terms of entropy of mixtures. Right, so that was it.